Every data engineer has been there. You have raw files sitting in S3, an Iceberg table waiting to be loaded, and a manual process that someone has to kick off every single day. In this series, we automate all of that. We will build a production-ready pipeline on Kubernetes using Apache Airflow to schedule the jobs, Spark to process and load the data, and Trino to query and verify the results, with full Iceberg snapshot history so you can time travel, roll back, and manage your data like a pro. If that sounds like what you have been looking for, stick around. Welcome to part 1 of our 4-part series on automating Iceberg data ingestion with Airflow, Spark, and Trino. In this video, we will set up the complete local Kubernetes environment that the rest of the series depends on. By the end of part 1, you will have all the infrastructure in place and ready to run a fully automated data pipeline. This series is a follow-up to our earlier guide on building a production-ready data lakehouse using Apache Iceberg, Nessie, Trino, and Spark on Kubernetes. In that guide, we set up the foundational Iceberg table and did an initial data load manually. Now we are automating that process. We will build a scheduled pipeline using Apache Airflow that reads raw Parquet files from S3, appends them into an Iceberg table, and commits a new snapshot to Nessie, all without any manual intervention. This series is broken into 4 parts. Part 1, which is this video, covers setting up the local environment. Part 2 covers creating the Airflow DAG and Spark application. Part 3 covers triggering the pipeline and verifying the results using Trino. And Part 4 covers working with Iceberg snapshots and data retention. Let us get started. In Part 1, we configure 5 things: the Kubernetes, namespace, NFS, shared storage for Airflow logs, Apache Airflow with Kubernetes Executor and Git Sync, the Spark operator, and the RBAC permissions for Airflow and Spark service accounts. Before following along, ensure these are already running. A kind cluster, S3 compatible storage such as MinIO or AWS S3, Nessie, Trino, and an existing Postgres instance in the MLOps namespace for Airflow's metadata database. All resources live in a namespace called MLOps. The setup command checks whether the namespace exists before creating it, making the script safe to run multiple times. Airflow runs tasks in separate pods, and each pod needs access to the same log directory. NFS Ganesha solves this by providing read-write, many persistent volumes that multiple pods can read and write simultaneously. Without this, task logs are written to each pod's local file system and never appear in the Airflow UI. We download the deployment, RBAC, storage class, and persistent volume claim files from the official GitHub repository. We then make 2 edits, setting the provisioner name in the deployment to match the storage class and pointing the export directory to a local host path. We apply the deployment and RBAC into a dedicated NFS provisioner namespace, then apply the storage class cluster-wide. After applying, we verify it appears with kube control get SC. Airflow orchestrates our Spark job with 4 key configurations. The Kubernetes Executor runs each task in its own pod, no Celery broker needed. Git Sync pulls DAGs from a private Git repository automatically every 60 seconds. Shared log storage mounts the NFS-backed volume across all worker pods. An external Postgres points Airflow at the existing database rather than a bundled one. We fetch the default Helm values file for the exact chart version using WAQ to parse the version automatically. This file serves as a reference. We only override the settings we need to change. Git Sync authenticates with an SSH private key stored as a Kubernetes secret. Make sure the matching public key is already added as a deploy key in your Git repository before running this step. The Airflow admin password is stored in a Kubernetes secret and injected at install time via an environment variable. This avoids hard-coding credentials in the Helm values file. Airflow's metadata database connection string, including username, password, host, port, and database name, is assembled from environment variables and stored as a Kubernetes secret. Airflow reads it automatically via the metadata secret name in the Helm values. The Fernet key encrypts sensitive values like connection passwords in Airflow's metadata database. Providing a stable key as a Kubernetes secret ensures those values remain decryptable across upgrades and redeployments. If Airflow auto-generates the key and it changes on the next deploy, previously stored encrypted values become unreadable. The API secret key signs Airflow's Web UI session tokens. Storing it as a stable Kubernetes secret means user sessions survive pod restarts and Helm upgrades without being invalidated. We create a persistent volume claim using the NFS Ganesha storage class with read-write many access. The NFS provisioner automatically binds it. All Airflow worker pods mount this same claim for shared log access. The custom values file ties everything together. Key settings, Executor is set to Kubernetes. Executor bundled Postgres is disabled in favor of the external metadata secret. Git Sync is configured with the SSH key secret, repository URL, and a 60-second sync interval. The log's PVC is referenced for shared log storage. Redis is disabled since we are not using Celery, and the create user job is configured to read the admin password from the secret at runtime. We install Airflow with Helm using the upgrade install command, passing our custom override. The Spark operator is a Kubernetes controller that manages Spark application resources. When the Airflow DAG submits a Spark application object, the operator launches the driver pod and handles executor lifecycle automatically. We install it from the Kubeflow Helm chart, capturing the default values first for reference. The only change from the defaults is the list of allowed job namespaces. Setting an empty string in the list allows the operator to manage Spark jobs in any namespace. For production, restrict this to specific namespaces. The only change from the defaults is the list of allowed job namespaces. Setting an empty string in the list allows the operator to manage Spark jobs in any namespace. For production, restrict this to specific namespaces. 2 RBAC configurations are required. The first grants the Spark operator Spark service account permission to manage pods, services, config maps, and jobs in the MLOPS namespace. These are the permissions the Spark driver needs to launch and manage executor pods. The second grants the Airflow-worker service account permission to create and monitor Spark application custom resources. This is what allows the Airflow task to submit the job. Both are defined as YAML files and applied with kube control apply. That wraps up part 1. We created the MLOps namespace, set up NFS shared log storage, installed Airflow with all required secrets, installed the Spark operator, and configured RBAC for both service accounts. In part 2, we write the PySpark script, build the Docker image, and create the Airflow DAG and Spark application manifest.